6 crew members, sealed habitat, air recycled continuously. The scrubbers are green. The oxygen is nominal. The CO2 reading is 1,200 parts per million, above Earth outdoor baseline, below any alarm threshold, within the operational parameters the system was designed to maintain. The crew's decision accuracy is already measurably lower than it was on Earth. Outside air contains roughly 400 parts per million of CO2. Humans evolved in that environment over millions of years. A Mars habitat running 6 people through a full sleep cycle will routinely exceed 1,000 parts per million during the hours when scrubbing output is reduced and respiratory load is highest. That number, 1,000 parts per million, is not a danger threshold. Nobody sounds an alarm at 1,000 parts per million. Nobody feels sick. Nobody notices anything. Controlled studies measuring cognitive performance in sealed office buildings show that decision-making accuracy drops measurably at exactly that concentration. The crew breathes it every night and wakes up slightly less capable than they were the night before. The air that keeps the crew alive is the same air that makes them slightly worse at keeping themselves alive every single day. The gap between those two facts, between the scrubber reading green and the crew operating at reduced capacity, is not a malfunction. It is the system performing exactly as designed inside a human biology that was never designed for it. CO2 is not toxic at the concentrations that cause cognitive impairment. That distinction matters because the entire architecture of atmospheric monitoring aboard spacecraft is built around the concept of toxicity, the level at which CO2 directly causes physiological harm, hypercapnia, acidosis, respiratory crisis. That threshold sits several thousand parts per million above where cognition begins to degrade. The alarm is calibrated to prevent medical emergency. It is calibrated at the wrong number to prevent impaired decision-making. Both of those statements are true simultaneously, and the monitoring system is not broken. The mechanism that produces cognitive impairment at subtoxic concentrations is not fully resolved in the research literature, but the effect itself is documented across enough independent studies that it is not seriously disputed. CO2 crosses into the bloodstream through the lungs and mildly acidifies the blood. The brain is sensitive to blood chemistry in ways that do not always produce conscious symptoms. The effect at 1,000 to 2,500 parts per million is not a headache or dizziness. Those come later at higher concentrations. The effect at the lower range is a reduction in the speed and accuracy of higher cognitive functions, working memory, the ability to hold multiple variables in mind simultaneously, and strategic decision-making under time pressure. A 2015 study published in Environmental Health Perspectives placed participants in controlled office environments at CO2 concentrations of 550, 1,000, and 2,500 parts per million and measured their performance on a validated cognitive function test. At 1,000 parts per million, scores on decision-making tasks dropped by approximately 15% compared to the 550 ppm baseline. At 2,500 parts per million, certain cognitive domain scores dropped by more than 50%. The participants were not told what CO2 concentration they were in. They did not report feeling different. They performed measurably worse without knowing they were performing worse. A crew member at 1,200 parts per million does not feel cognitively impaired. They feel normal. Their error rate on complex tasks is measurably higher than it was at 400 parts per million. The measurement requires a test. The subjective experience does not require a test and does not report the problem. The crew member making worse decisions is also the crew member who has no internal signal telling them their decisions have degraded. The monitoring board reports all green. The impairment is not on the monitoring board. In 2021, crew numbers aboard the International Space Station reported persistent headaches and fatigue that were eventually traced to CO2 levels in the Russian segment of the ISS running consistently above 5,000 parts per million. The source was a degraded carbon dioxide removal system that had been operating below specification for a period measured in months before the levels were definitively attributed and the cause identified. 5,000 parts per million is 12.5 times the outdoor Earth baseline. It is 5 times the concentration at which cognitive impairment studies show measurable decision-making degradation. It is still below the threshold at which the monitoring systems aboard the station are calibrated to produce emergency-level alerts. The crew had been living and working in that atmosphere for months. They reported the symptoms. The investigation took time. The ISS incident is not an isolated data point in the history of crewed spaceflight. The station has documented CO2 exceedances above 2,500 parts per million during normal operations on multiple occasions across its operational history, not during failures, but during periods when the life support systems were functioning within their design parameters. The design parameters were set based on medical safety limits, not cognitive performance limits. The gap between those two sets of limits is not a small engineering margin. It is a range of CO2 concentrations from roughly 1,000 to several thousand parts per million, in which a sealed habitat can operate indefinitely without triggering any alarm, while the people inside are performing measurably below their own baseline. The ISS has already shown that real missions, operated by trained crews with full ground support, routinely spend time in that range. A Mars habitat will spend more time there, with less support, with no option to open a window. The ISS has resources that a Mars habitat does not. When CO2 levels rise above acceptable thresholds on the station, mission control can respond within minutes. Resupply missions carry replacement scrubber chemicals on a schedule measured in months. Equipment that degrades below specification can be identified, reported, and addressed with the full engineering resources of multiple national space agencies operating in real time. The station is 8 minutes from Earth by radio. Earth engineering teams can analyze data, develop procedures, and upload solutions on a timeline measured in hours. A Mars habitat is between 3 and 22 minutes by one-way radio signal. Round-trip communication lag at Mars ranges from 6 minutes to 44 minutes, depending on orbital position. A crew responding to an atmospheric anomaly cannot consult mission control and receive guidance before the situation has already developed further. Every decision about how to respond to a CO2 exceedance, whether to reduce crew activity, redistribute scrubber load, switch to backup systems, or begin emergency procedures, must be made by the crew using their own judgment. The crew whose judgment is being reduced by the CO2 concentration they are trying to manage. The failure chain that starts with elevated CO2 does not require a dramatic threshold to be crossed. It requires a series of small decisions made slightly less accurately than they would have been at 400 parts per million. A system anomaly noticed slightly later than it would have been. A diagnostic reading interpreted with slightly less precision than the situation required. A response initiated slightly too slowly to prevent the anomaly from compounding. None of those decisions look wrong in the moment. None of them trigger any automated system. Each one is within the operational envelope of a normally functioning crew. The cumulative effect of many small decisions made at reduced cognitive capacity over a mission measured in years, in an environment where no individual decision looks like a failure, is the actual risk profile. It does not present as a crisis. It presents as a mission that is slowly, quietly going less well than it should. There is also a compounding dimension that the CO2 concentration numbers alone do not capture. Cognitive impairment from elevated CO2 accumulates most during sleep, when scrubbing output is reduced and metabolic CO2 production from 6 sleeping crew members continues at its resting rate. The crew wakes having spent 8 hours in the highest CO2 environment of any part of their daily cycle. They make the first decisions of the day, system checks, anomaly reviews, scheduled maintenance decisions, at the lowest cognitive capacity of their daily cycle. The decisions made at the start of each day, on a mission where the start of each day follows 8 hours of peak CO2 exposure, are the decisions made with the most impairment. Mission planning does not currently model this exposure pattern as a cognitive risk factor in crew scheduling. There is a particular quality to cognitive impairment that makes the CO2 problem harder than a simple engineering gap. Most physiological hazards in a spacecraft produce signals the crew can detect. Radiation exposure produces no immediate sensation, but dosimetry hardware tracks it continuously, and the number goes up visibly. Bone density loss produces no immediate pain, but periodic scans show the progression, and the crew knows the clock is running. CO2 cognitive impairment produces no external measurement and no internal sensation. It produces only the impaired judgment that would be required to assess whether judgment is impaired. The crew member whose working memory has degraded by 15% is not slower to think. They are not confused. They do not feel different from yesterday. They process the same tasks at the same subjective effort level and arrive at answers that are, on average, slightly more likely to be wrong. The error is invisible to the person making it. This is the specific mechanism that makes the problem resistant to behavioral solutions. Training crews to recognize CO2 impairment requires the unimpaired crew to establish a cognitive baseline, and then requires the impaired version of the crew to compare their current performance to that baseline accurately, which is precisely the higher-order metacognitive function that elevated CO2 degrades first. The crew cannot reliably self-report a deficit in the cognitive functions they would use to report the deficit. The engineering response to CO2 accumulation in a sealed habitat is additional scrubbing capacity. More scrubbers, running more continuously, processing more atmosphere per hour, keeping the concentration lower. This is correct in principle and constrained by mass in practice. Every kilogram of scrubber hardware and consumable chemicals launched to Mars costs propellant. Every kilogram of propellant costs more propellant to lift it. The mass multiplication that the rocket equation applies to every payload item applies to life support hardware at full force. A Mars mission with sufficient redundancy for scrubbing to maintain habitat CO2 below 550 parts per million under all operating conditions, including peak crew activity, scheduled scrubber maintenance windows, and unscheduled equipment degradation, would carry a substantially larger scrubbing system than a mission optimized for mass efficiency. The mass penalty for that redundancy comes directly from some other mission component: science equipment, emergency medical supplies, habitat volume, return vehicle fuel. The decision about how much scrubbing redundancy to build into a Mars habitat is not made by looking at cognitive performance thresholds. It is made by weighing cognitive performance margin against everything else the mission requires and cannot carry because the scrubber hardware took that mass allocation. For every Mars mission architecture currently under development, the outcome of that calculation is a scrubbing system designed to maintain CO2 below medically dangerous levels with operational redundancy for failure scenarios, not a system designed to maintain CO2 below cognitive impact thresholds under all conditions, including routine operations at peak metabolic load. The ISS approach, accepting periodic exceedances as operationally normal and managing them through monitoring and activity reduction, translates to Mars with one critical modification. The monitoring and activity reduction decisions are made by the crew whose cognitive capacity is reduced by the exceedance they are managing, without real-time support from Earth, on a timeline that does not permit the kind of extended troubleshooting process that resolved the 2021 Russian module problem over multiple months of ground team investigation. On the ISS, a degraded scrubber is a problem the mission control helps solve. On Mars, a degraded scrubber is a problem the crew solves alone at the CO2 level the degraded scrubber produces, with whatever cognitive capacity that level leaves them. The cognitive threshold is not a number the mission can negotiate with. It is a biological constant set by human neurophysiology, which was not consulted when Mars mission architecture parameters were established. The engineers designing the scrubbing system are working against a number, 1,000 parts per million, that does not appear in the medical emergency protocols, does not appear in the alarm calibration tables, and does not appear in the operational safety margins the system was designed to maintain. It appears in cognitive performance research conducted in office buildings and schools, where the question under investigation was why workers in sealed conference rooms made worse decisions after 2 hours than they did in the first 30 minutes. The answer to that question, that CO2 from shared breathing accumulates faster in a sealed room than ventilation removes it, and that the accumulation is cognitively significant at concentrations that feel completely normal, is the same answer that applies to a Mars habitat. The difference is that the conference room worker can step outside. The Mars habitat crew cannot. The outdoor air on Mars is 95% CO2 at a pressure too low to breathe. The sealed habitat is not a temporary inconvenience. It is the only environment available for the duration of the mission. The cognitive exposure that a conference room worker accumulates in a 2-hour meeting is the cognitive exposure that a Mars crew accumulates every night, every morning, and every working hour in between. NASA's current Mars architecture planning documents identify CO2 management as a solved problem within the life support system design. The scrubbing targets specified in those documents are calibrated against physiological safety thresholds. The gap between those targets and the cognitive impact threshold is not identified as an open engineering problem in the same documents. It sits in a different literature, cited in different journals, read by different researchers, and not yet translated into the mass specifications that determine how much scrubber hardware a Mars mission carries. The air is clean. The scrubbers are green. Somewhere between 400 parts per million and the number on the habitat monitor, the crew is making decisions that are slightly worse than the decisions they came to Mars to make, and the system that was built to protect them will not tell them.